Feel free to ask me any questions if you have any, Rylan. I'm just trying to get our affairs in order on my Canvas class. Uh, Anybody here yet? Hey, Mackenzie, feel free to ask questions while you're waiting. We got about 6 minutes before class starts. It's only you and one other student here. About 5 minutes now. All right, we got about 2 minutes left, everybody. Feel free to ask me questions as you wait. Another person came in. All right, about time to start. All right, everyone. So let's go ahead and get started. It is time. It's actually 5:31. I was just writing up some facts and things to help you with chapter 21. That's what we're going into. Uh, I gave you a little intro to what charge was, the fact that it was positive and negative, telling you that the charge was measured in coulombs. And I think I even, let me double check this. Yeah, I actually gave you the formula for the Coulomb's law for the electric force, and I gave you, of course, reminded you the formula for the gravitational force from Newton's law of gravity. And I suggested there was an extra credit you could get by comparing the electric force of attraction between the electron and the proton to the electric force of attraction, or excuse me, between the gravitation between it and the gravitational force between the electron and the proton in a hydrogen atom. So I'm just writing that up right now. Let me go ahead and finish that, and I'm going to share the screen so you can see it, because we're going to roll right into working with Coulomb's law. So I'm now sharing my screen. Might take a couple seconds for it to get up there. But the first thing I ask you to do is calculate the gravitational attraction between the electron and the proton in a hydrogen atom in the ground state. And I don't know why I used an N on the end of that atom instead of an M. But let me fix that real quick. In its ground state. B, do the same thing for the electrical attraction. And I'm going to call this one F sub G. I'm going to call this one F sub E. And then part C, I want you to calculate F sub E over F sub G equals question mark. Okay, so you can get a real idea for how much bigger the electric force of attraction between the electron and the proton in a hydrogen atom is compared to the gravitational force of attraction between the electron and the proton. And that's just another extra credit problem you can do, and it's a simple application of Coulomb's law. So now that I've done that, let me go ahead and separate from that section, which was really just a chance for me to show you an extra credit problem. But now let me remind you what Coulomb's law is. So Coulomb's law says that the force of attraction gravitationally is equal to, and I'm going to use a K here, but I really honestly hate the K. I don't use the K hardly at all, but that's initially what your book usually starts off with. So basically what they're saying is the force of attraction or repulsion is proportional to the product of the charges. So that means it's directly proportional to Q1 and Q2, and they're supposed to be point charges. And it's inversely proportional to the square of the distance between them. And this K is actually equal to 8.99 times 10 to the ninth. And of course, those units turn out to be newtons, meters squared per coulomb squared. But to be honest with you, what I normally like to write is Q1, Q2 over 4 pi epsilon naught r squared, where epsilon 0 is equal to 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. And that's using what's called the permittivity of free space. Let's see, John just came in. Let me mark him. Okay, so that's a version of Coulomb's law. And I want to tell you that the way Coulomb's law works is just like the way gravity works. Remember, at the time of Newton, and of course even later when we do Coulomb, for instance, the idea of a vector wasn't quite formed yet. People hadn't even thought about vectors in the time of Newton. But by the time of Coulomb, we're getting closer to the time period, which is roughly somewhere between the 1830s and the 1860s, is when we actually conjured up the idea of vectors. And Oliver Heaviside and a person from America, who I think is, I forget his name, but anyways, he's one of the people who's got an energy named after him in thermodynamics. That particular guy, I want to say Gibbs or something like that. It might be Gibbs free energy or whatever. But those two people independently invented what we call vector calculus and vector algebra and all that stuff. So that would have happened roughly around the 1830s to 1860s. And the way you would do something prior to that is you'd have to tell not only what variables depended on what other variables in what way. So you'd say the force is directly proportional to the product of the charges and inversely related to the square of the distance between the charges, and it acts along a line connecting the center of charge of the two charges. Okay, so that's really what we're talking about here. The force, whether it be attractive or repulsive, is going to act along the line from the center of charge of Q1 to the center of charge of Q2, and it's directly proportional to the product of Q1 and Q2 and inversely proportional to the square of the distance between them. So those are all the key words you need to understand and know about Coulomb's law, and for that matter, about the law of gravity. So what I'll tell you is Q1 greater than 0 and Q2 greater than 0 implies repulsion, or repulsive force. Okay, Q1 less than 0 and Q2 less than 0 again implies a repulsive force. And then Q1 less than 0 and Q2 greater than 0 implies a attractive force. And Q1 greater than 0 and Q2 less than 0 also applies an attractive force. Okay. The force acts along the line connecting the center of charge, of Q1 and the center of charge of Q2. The R is the distance between those two centers of charge. Okay, so that's one principle. There's another 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 principle. Okay, so that's really all you need to really know, for instance, to work out what the force is for a Coulomb attraction or a Coulomb repulsion. What I'll tell you also is you should almost never enter the signs of the charges into Coulomb's law. Just enter both as if they are positive. Okay, so that's just something I've learned over the years, that it's best to not try to plug in a negative 1.0 times 10 to the negative ninth coulombs for Q1 and a positive 5.0 times 10 to the negative 6 coulombs for Q2. Don't put the signs in. Just assume they're both positive. Use the actual calculation using the formula to just come up with the actual magnitude of the force. Draw a picture representing the diagram that would, well, draw a picture representing the physical thing that you're studying, showing the two charges that are attracting each other, embedded in some kind of coordinate system of your choosing, and then just compute what the magnitude is. And all you have to do is then draw a line from Q1 to Q2. If they're point charges, you just draw it from Q1 to Q2 or from Q2 to Q1, doesn't matter. And you know the force of attraction or repulsion will lie along that line. So you've got it. That's how you use it and figure it out. Don't put in a negative sign. Just assume they're both positive. Compute the time, and then make a note to yourself. Hey, the two charges are the same sign, so it's going to be repulsive. Or hey, the two signs are opposite, so it's going to be attractive. And then you have to think about, okay, well, if it's an attractive force and we want to know the force on charge Q1, then since it's attractive, that would be a force on Q1 that points towards Q2. Whereas if it's a repulsive force and you're asking for the force on Q1, then you're going to see that the force would be pointed away from Q2 towards Q1. That's the way you do it. So anybody have any questions on that? Now, I gave you an extra credit problem, and you'll see that example 21.1 basically gives you part of the answer already. So example 21.1 in your textbook is using Coulomb's law to calculate exactly what the force of attraction is between an electron and a proton. And they're even so kind as to give you the actual average distance between the electron and the proton in a hydrogen atom. Okay. So they've given you that. They gave you what the actual charge was. They're actually only using 2 sig figs, but that's okay as well. So that's sort of your first most rudimentary example of applying Coulomb's law. And in that case, you're not even thinking about the object in three-dimensional space. You're just really trying to calculate the magnitude. So a lot of times you don't even draw a diagram if you're doing something like that. There's a conceptual example it asks in example 21.2. It says two positive charges, Q1 equals 50 microcoulombs and Q2 equals 1 microcoulomb, are separated by a distance L. Which is larger in magnitude, the force Q1 exerts on Q2 or the force that Q2 exerts on Q1? Can anybody, again, I just read that, so there's some possibility that maybe y'all weren't paying close enough attention to know what I said, but does anyone know the answer to that just from the one time I said it? I'm going to read it again to you now so you can pay more attention, but see if you can answer this question. Two positive point charges, Q1 is equal to 50 microcoulombs, and Q2 is equal to 1 microcoulomb, are separated by a distance L. Which is larger in magnitude, the force that Q1 exerts on Q2 or the force that Q2 exerts on Q1? Anybody think they can answer that? I'm going to turn on the chat so I can actually see if anybody types it as opposed to just speaking. Anyone? Sebastian says the same. Yes, absolutely. That is essentially a statement of Newton's third law. Newton's third law says that F12 is equal to negative F21, which means the force on object 1 as a result of object 2 is equal in magnitude and opposite in direction as the force on object 2 as a result of object 1. So if you just reverse which one's the force creator and which one's the force receiver, then they're equal in magnitude but opposite in direction. So yes, it's the same. So good job, Sebastian. Make sure I got you marked off in here. Yes, I do. Okay. So there's an example Q2. Let me go ahead and show you another example. What we're going to have is 3 charges in a line. So let's do this one. I will start off by drawing a line to separate the facts that I just wrote down from the actual problem we're getting ready to solve. So there's my line, and I'm going to draw a picture. We've got 3 charges. I'm going to draw them along this line right here, say. And this charge right here is going to be a negative charge, and it is Q1 is equal to negative 4.0 microcoulombs. Then right here is going to be a positive charge, and this one's going to be Q2 is equal to positive 3.0 microcoulombs. And then there's going to be a charge over here, and that one's going to be negative, and that's Q3 is equal to negative 8.0 microcoulombs. Okay, and let's just call this the x-axis just for concreteness. We don't really have to have any particular thing, but it could be any axis we want. What I'm going to tell you is these charges that we're talking about are point charges, and this one is 0.30 meters between Q1 and Q2, and between Q2 and Q3 is going to be 0.20 meters, like that. And what I would like to do is calculate the net electrostatic force on particle 3. So what is F on Q3? Okay, so the solution goes like this. What we have to remember is the electric force is a force like other forces we learned about, and therefore it has a vector quantity. It's a vector quantity, so it has a magnitude and direction, but it is a sum of other forces. So for instance, specifically F3 as a vector is equal to the force on 3 as a result of 1 plus the force on 3 as a result of 2. Now, I don't have to write the force on 3 as a result of 3 because, anyone? Oh, thank you, Ava. I see you found it. Good job. Does everybody know why I did 3-1 and 3-2, but I didn't do 3-3? Okay, so the main point here is, according to Coulomb's law, we have a force of attraction or repulsion that's proportional to the product of the 2 charges and inversely proportional to the square of the distance between them. Okay, so we've got a way of grouping up in 2, so that's why we have to have F31, for instance, which is the force on 3 due to 1, and then F32, which is the force on 3 due to 2. But we don't need a force on 3 due to 3 because obviously forces, charges can't apply forces to themselves no more than you can, grab yourself by your shoestrings and pick your whole body up, right? So that's what's going on here. Now, the important thing is, as I told you, I want to use F is equal to K Q1 Q2 over R squared, and I don't want to put the signs in, but I do want to make sure I understand that it's a vector quantity. So what I need to think of first is in which direction is F31. So when I'm talking about F31, remember that's the force on Q3 due to Q1. Okay, that's key. I want you to understand that terminology that I'm using with the subscripts, because that's going to go on and on and on. So make sure you know that now. Now, what I see is Q1 and Q3 are both negative. So does that mean it's a repulsive force or an attractive force? No one typed an answer on that one. So Q1 and Q3. Go ahead.
Repulsive.
Did you say repulsive, Sebastian?
Yeah.
Yeah. When they're like charges, they're repulsive. So what that means in this diagram is that the force on 3 due to 1 is going to point to the right. So F31 points right. Now, that's a very specific thing I'm saying there. What I'm telling you is since the positive x-axis points to the right, this F31 is going to be some number times some positive number times I hat, or some positive number times x hat. Does everybody get that? And now I'm going to do F32, which is the force on Q3 due to Q2. Now, Q2 is a positive charge, so that's greater than 0, and Q3 is still less than 0. So is this force attractive or repulsive?
Attractive.
Yes, it'll be attractive. And what that means is the force on Q3, which is the one to the far right, that force on Q3 will point to the left. So points left. Okay. Now, just so we make sure we can read all of this, I'm going to kind of clear this up a little bit and say Q3 is equal to that. And then I'll also finish this by drawing those arrows back so we know what's going on. So I just want to make sure that was clear. Wow, I really made that Q3 small. Let me make it a little bigger than that. I'm going to say, whoa, Nelly. I'm going to say Q3 is that quantity. So now I'm going to go ahead and use those facts. The fact that they point to the right and left means that basically these two are fighting, and the one with the biggest magnitude wins. So I would call the F31, which points to the right, a positive force. And I call the one that points to the left a negative force. And whichever has the biggest magnitude wins the sign war, and therefore it'll point that particular direction. So can anybody guess ahead of time which one's going to have the bigger force, the F31 or the F32?
The F32.
Yeah, the F32, because the Q3 and the Q1 is 8 times 4, which is of course 32, but then the distance is 0.5, whereas the F21, or excuse me, 23, 32 is going to be 3 microcoulombs and 8 microcoulombs. So that's 24, but the distance is only going to be 0.2. So that's going to be a bigger thing is what I would suspect. So now we just have to calculate it. And that's largely what we do with Coulomb's law is we use it to just calculate a magnitude. So I'm going to say F31 is equal to 8.99 times 10 to the ninth. I'm going to leave the units off. We've seen how they work out. I'm going to also leave the signs off because that's what I told you. You should almost never enter the signs. Almost never enter the signs. So 3 and 1 is going to give me Q3 is 8.0 times 10 to the negative 6. That's what micro means. And Q1 is 4.0 times 10 to the negative 6. And then the distance between them is obviously Q1 and Q3 is always all the way at the opposite end. So I'm going to say 0.50 meters. And then that quantity, of course, has to be squared. So when I compute this, I'm going to say 8.99 e to the ninth. Notice I'm carrying one extra sig fig than they gave me, so I'm really kind of safe doing this. I said 8.99 times 10 to the ninth times 8 e to the negative 6 times 4 e to the negative 6. And then I'm going to divide that by parenthesis 0.5 squared. It's in meters, so everything works out fine. So this force turns out to be 1.151. That's 2 sig figs more than I actually can have. So it's only 2 sig figs, and I've got 4 digits I've written down here. And because the K had units of Newton meter squared per Coulomb squared, the Coulomb squareds cancel out with the 8 and the 4. The meter squared cancels out with the 0.5 squared in the bottom, so I just get Newtons. And this is the one, the 3-1 is the one we said points in the positive direction. So I'll just put that up here to remind us that it's the positive direction. Now I'm going to do F32. And that again is 8.99 times 10 to the ninth. Q3 is still going to be 8.0 times 10 to the negative 6. But now I use Q2, which is 3.0 times 10 to the negative 6. And then these two guys are a lot closer to each other. They're only a distance of 0.20 meters, and that's going to be squared, of course. So in this case, I get 8.99 e to the 9 times 8 e to the 6, or excuse me, e to the negative 6 times 3 e to the negative 6. And now I'm going to divide all that by parenthesis 0.2 squared, close parenthesis. Didn't really have to use that there. But in this case, I get 5.394 newtons, which again is 2 extra digits than we actually have as sig figs. Neg direction. Okay, so F3 is just going to be basically, notice the negative direction is what wins. So I'm going to say to the left. And the force is going to be 5.394 minus 1.151. And that's going to give me 4.243 newtons. And notice I did say explicitly it points to the left. So that's our answer. Anybody have any questions on that? Okay, so that's how you have to deal with this. When you're dealing with more than one, you just have to consider the force between the one that you want to know the force on and one of them. And if they want to know the total force, then you're going to have to do that for each of the other charges. Just like I did in this case, there were three charges, and I wanted to know the total force on three. So I had to do the force on three due to one, and then I had to do the force on three due to two. If there was five of these, I'd do the force on three due to one, the force on three due to two, the force on three due to four, and the force on three due to five. So that would give me four terms. And these are all linear, they're all along the same line. So that's how I knew it's either going to be left or right in terms of direction. Then it's just a matter of deciding whether it's attractive or repulsive to decide whether or not you get it pointing to the left or to the right. Does anybody have any questions on this? Okay, so I'm going to do another example. That was example one, say. Okay, so now I'm going to do another example. We're going to call this example two. And what I'm going to do is I'm going to consider a couple different scenarios. So first off, I'm going to draw a coordinate system just because that makes it unambiguous exactly what you're supposed to answer to me. And I'm going to say this is my x-axis right there. I'm going to say this is my y-axis right there. What I'm going to do is I'm going to put a charge, let's say right here, and I'm going to put another charge, let's say right here. And these two charges are going to be equal in magnitude but opposite in sign. And when you have such a thing, this is called an electric dipole. Okay. So when you have two charges just separated by some distance apart, and one's positive and the other one's negative, but they have the same magnitude, then that's what we call a electric dipole. And it's something that comes in handy from time to time. You can sort of think of it as there's a bunch of different poles. There's a dipole, and there's a quadrupole, and then there's an octopole, and then there's a sixteenapole, that sort of thing. So powers of two get you poles. And if you try to, for instance, calculate a force like a Taylor or Maclaurin series, like you did in calculus, then you can almost always reduce it down to a sum of poles, which would be a dipole plus a quadrupole plus an octopole plus a 16 pole plus a 32 pole, a 64 pole, so on and so forth. So that's one of the reasons it comes in handy. And in fact, sometimes using that kind of separation, you can make something that's closer to a sphere than an actual machinist can make a sphere. So that comes in handy sometimes as well. What I'm going to do is I'm going to say that, yeah, I'm going to say that this particular one on the right is 1.5 centimeters from the origin. And this one on the left is negative 1.5 centimeters. And that means the distance between them is really 3.0 centimeters. And now I'm going to put another charge. Hypothetically, I'm going to put another charge right here. And this one is at positive 4.0 centimeters. Okay. But I say temporarily because I'm also going to consider it being right there on the y-axis, and I'm going to calculate the force on it in both places. So in A, I want to know this one, and in B, I want to know the force on the charge when it's there. So what is the electric force on, and let's call this guy, this one's going to be called Q1. Oh, actually, I don't want to put it like I did right there because it looks like it's suggesting the value of Q1 is negative 1.5. So I didn't want that. So this guy right here is going to be Q1, and this guy right here is going to be Q2, and then this guy up here is going to be Q3, and again Q3. So what is the force on Q3 at, in this case, it's going to be x equals 0 or x equals negative 1.5 and y equals 4.0 centimeters. And part B on Q3 at 0, 4.0 centimeters. Okay, so this up here says 4.0 centimeters is the y and negative 1.5 is the x. So that's what we're going to try to calculate. So my solution is going to require us to know some things. For instance, we're going to need to know Coulomb's law, which I'm going to say is F is equal to K, Q1, Q2 over R squared. I'm also going to have to know, for instance, what is F3, and I'll put a sub A on it for part A. Well, F3 is the force on 3 due to 1 plus the force on 3 due to 2. And then similarly, F3 sub B is also the F3(1) plus F3(2). But notice the difference in both cases is the fact that the Q3 is in a different place. Okay. So the first thing that we generally calculate when we're doing these forces is just calculate the magnitude, and then we use our diagram to figure out what vector that makes. So let me go ahead and calculate for part A. So here's part A. Q3 is at negative 1.5 centimeters, comma, 4.0 centimeters, and therefore F3(1) is equal to 8.99 times 10 to the 9th. Now it's the charge 3, which I haven't given you, so I should probably do that now. Let's say let's say it's 6. I'm going to say Q3. And I didn't give you the other one either, so okay, that helps me. Okay, so Q3 is going to be equal to, let's say, 3.0 times 10 to the negative 3 coulombs. Q1 is going to be my positive charge, and I want to say that's positive 3.0 times 10 to the negative 6 coulombs, and Q2 is equal to negative 3.0 times 10 to the negative 6 coulombs. So when I say 3(1), what I mean is I'm going to say charge 3, which is 3.0 times 10 to the negative 3rd coulombs, times 3.0 times 10 to the negative 6 coulombs. And then the distance between 3 and 1, notice that's exactly 4.0 times 10 to the negative 2 meters. And then I got to square it. Okay. Now you might notice that I took a little time to think exactly what charges I was going to be using. The reason I did that is ideally, I would like, well, Uh, Ideally, it's really nice if I can get rid of the 9 times 10 to the ninth. So by using a 10 to the negative third and a 10 to the negative six, I get rid of the 10 to the ninth. That's helpful. If I'd use 0.333 and then 0.333 for the two mantisses of those charges, then that'd be 1/3 times 1/3, which would be 1/9, and that would actually calculate the cancel out the 8.99 as well. I chose not to do that this time, but anyways, that's an ongoing goal. Is sometimes you can make the numbers a little easier. In this case, I'm going to get 9 times 9, which is 81, but then I'm going to multiply it by 100 and then divide it by 4, so or 16. So we'll work that out. What I get is 8.99 e to the 9 times 3 e to the negative 3 times 3 e to the negative 6. And then that, of course, gives me 80.91. And then I'm going to divide that by 0.04 squared. And that gives me 80.91, which notice the two sig figs would have been 81 over 0.04 would be 16 over 10,000. Okay, so that's really what the numbers work out to be. When I actually divide that, though, I get 5.057 times 10 to the 5th newtons. And that is, of course, 2 extra digits than the sig figs allow. Everybody see that that's 5.057? I wrote it kind of small. Times 10 to the 5th newtons. Now, it's important to understand exactly what charge is that. Notice Q1 is positive, and notice that Q3 is also positive. So the two forces are fill in the blank, repulsive or attractive. Or the force is repulsive or attractive, not two forces. Say it one more time.
Repulsive.
Exactly. So that means, remember, they always act along the line connecting them. So the line that we're thinking of right now is this line. And in fact, it points in the positive y direction. So I'm going to say that's our force, F31, right there. Okay. When I do F32, that's going to be along that line. Okay, because that's the line that connects them. So I now have the magnitude of F31 for part A, and now I need the magnitude of F32. So F32 is going to be equal to 8.99 times 10 to the ninth times Q3, which is, of course, 3.0 times 10 to the negative third coulombs. Now, this time it's the same number, but it's going to be a negative. So that just means it's an attractive force as opposed to repulsive. But notice I do not write the sign in there. I don't want you writing the signs in there. That only leads to problems. But in this case, it's going to be times 10 to the negative 6. And then all of that is going to be divided by. Can anybody tell me how many centimeters that diagonal or that hypotenuse is? I bet you know.
5 centimeters.
Yeah, it's the basically the 3-4-5 triangle was what I was trying to use. So I'm going to write that as 5.0 times 10 to the negative 2 meters. And then I'm going to square that. And I don't know why I chose to write the meters in there when I was distinctly trying not to put the units in, but here we are. So this one's going to be 80.91 again over, and this time it's going to be 25 over 10,000. Okay. So I'm going to do divided by 0.05 squared in parentheses, and that gives me 3.236 times 10 to the 5th newtons. So again, I've written 2 extra digits beyond what the sig figs justify, so we can make sure we're keeping all of our forces or all of our numbers to a couple extra sig figs in the intermediate calculations. Now, in this case, the Q2 is negative and the Q3 is positive, so they are attractive. And in fact, here it's kind of a bummer because this vector doesn't point parallel to any axis. So I'm going to make it in purple. I'll use red and green to indicate positive and negative, red being negative and green being positive. But that's our F3 2 right there. And since we know it's a 3, 4, 5 triangle, then we know that the 4 is opposite here. And this is going to be an angle of tangent inverse of 4 divided by 3, which is that 53.13 degrees. So I'm going to write this right here is 53.13 degrees. So that allows me, in actuality, to find a component of the vector pointing, remember, we're going to start at the tail of the vector that we want. So what we want to do here is we want to find the components of F32. F32, if I start from the tail of it, which is that black dot where Q3 is in part A, and move parallel to the X and Y axes to the head, then I either go down first and then I go right, which happens to be, in this case, in a positive direction, like that, or I go right first, which would be a positive direction, followed by down, which would be a negative direction. But you see that I get those 2 vectors, the red guy and the green guy. So the red one, I'm going to get my marker back on red. This guy right here is actually equal to F32 times the sine of 53.13 degrees. And this guy, the green one there, notice the angle theta ends up over here. So that means the adjacent is the green one. So that's why I'm using cosine there and sine for the red one. So for this guy, that's going to be F32 times the cosine of 53.13 degrees. And of course, it points to the right, so that one's going to be a positive, but the other one points down, so that one's going to be a negative. So I can now say F31 as a vector. Notice F31 points purely in the y direction. So I can call F31 5.057 times 10 to the 5th newtons. And then I just put a j hat after it. So that's a complete vector already just by writing the j hat after it. Everybody remember your I hat, j hat, and k hat? I can write F32 x component. That's going to be a positive. Notice it's the green one. That's going to be a positive, and I'm going to take the 3.236 e to the 5th, and I'm going to multiply it by the cosine of 53.13. And that's going to give me, holy Jesus. Oh, yeah, that's right. So 1.942 times 10 to the 5th newtons positive is the x component. F32y, that one's got to be a negative, so I force the negative right here. Notice how I'm forcing these signs in there, and notice how I'm not using negative angles, negative charges, positive charges. I'm not paying any attention to those signs. In this case, I'm going to take F32, which is 3.236 e to the 5th, and I'm going to multiply it by the sine of 53.13, making sure I'm, of course, in degree mode. And that's going to give me 2.589 times 10 to the 5th newtons. And of course, the 8 and the 9 are not sig figs. So now I can say that F32 is equal to, I'm going to put the y first just because I have a y component directly above it, so it's smart to do it that way. So in this case, I'm going to say negative 2.589 times 10 to the 5th newtons j hat plus 1.942 times 10 to the 5th newtons I hat. Okay. And of course, the 8 and 9 are not sticking together. So if I take 5.057 minus 2.589, then I get 2.468. So F3 is equal to 1.942 times 10 to the 5th newtons in the I hat direction, because it didn't have an I hat to add to it. So I just wrote that one down as it is. When I subtracted 2.589 from 5.057, I got positive, I got positive 2.468 times 10 to the 5th newtons in the j hat direction. So now I'm writing it in the normal order, which is I before j. Okay. So that's my actual force. And in fact, notice they're both the same magnitude, 10 to the 5th, and one's about 2.5 and the other one's about 1.9. So they're pretty close to the same size, and they're both positive. So I could, for instance, draw a little coordinate system. That's what I'm going to do here. There's my x, there's my y. Notice my x and y are completely consistent with the original coordinate system I had. The x component is going to be about 2. So what I'm going to do is I'm going to say, here's a vector that's 1.942. And then here's another vector that's 2.4. Notice it's a little bigger, 2.468. I'm ignoring the 10 to the 5th because that's going to cancel out, but it's the same thing. So what I'm going to say is the actual resultant vector, F3, is this guy at an angle phi. So I can say F3 can also be written as, I'm going to take 1.942 and I'm going to square it. That's only supposed to have 2 sig figs, so that gives me 3.771. So really, I get 1 decimal place. Now I'm taking 2.468 and we'll square that. That gives me 6.09, so I get 1 decimal place on that. So I'm going to say that plus 3.77. So I get the square root of 9.86. Okay, that's how I got the magnitude, by basically doing the Pythagorean theorem. So I'm going to take the square root of that, and that gives me 3.140. times 10 to the 5th newtons. And now I'm going to say it's at, now I'm going to take the inverse tangent, which I'll write in blue over here. I'll say tangent of phi is equal to the tangent inverse of 2.468. Remember, it's times 10 to the 5th, but that's going to cancel out the top and bottom, and 1.942. Again, I've got extra sig figs there. I'm only supposed to have 2 sig figs. So I'm going to take the inverse tangent of 2.468 divided by 1.942, close parentheses, I get 51.8 degrees. So I'm going to say this is at 51.8 degrees. So what I've now computed is the force F3 for part A 2 different ways. I've done it in the IJK notation, and now I've done it in the magnitude and the magnitude direction method. Anybody have any questions on that? All right, now for part B. What we want to notice again is that, crap, really getting frustrated with this. F3 for part B is F31 plus F32. Okay, so I'm going to go ahead and calculate F31. That's going to be 8.99 times 10 to the 9th. And then, of course, that's going to be times 3.0 times 10 to the negative 3 and times 3.0 times 10 to the negative 6. Now, in this case, the distance is a little odd. I'm going to have to go to the right 1.5 centimeters. If I'm going from Q1 to 3, for instance, I'd go to the right 1.5 centimeters and then up 4. So I've got to figure out what that is. And if I'm doing the 3, 2, then I have to go to the left 1.5 centimeters and up 4. But luckily, that's going to be the same for both forces. Oops. That's going to be the same for both forces. So at least I'll have the same denominator. The denominator is going to be the square root of 1.5 squared plus 4.0 squared square root times 10 to the negative 2. That makes it into meters. And then I'm going to square all that. We know the top is going to give us 80.91 because it's the same thing as we did before. So I'm going to say divided by parenthesis. I'm going to say square actually the square root is going to be canceled by the squaring. So I'm just going to say 1.5 squared plus 4.0 squared. That takes care of the squared part. And then I'm going to say times 10 to the negative 4, because that'll fix the actual fact that I got to square the 10 to the negative 2. So I'll say times so I basically said 80.91 divided by parenthesis, 1.5 squared plus 4.0 squared, close parenthesis, times 1 e to the negative 4. And that takes the place of squaring everything. So I get 4.43 times 10 to the 5th. That's one extra sig fig this time, and that's plenty for me. What I'm going to notice now is that F32 is going to be the same thing. They're actually going to have exactly the same magnitude. So Actually, instead of writing that down there, I'm just going to say, hey, this is also equal to F32. Does everybody see that F32 and F31 have to have the same magnitude? Now, in this case, the force F31, since the Q3 is positive and the Q1 is positive, it's going to be repulsive. So I'll write up here, I'll say that's F31 because it's repulsive. But F32, since the Q2 is negative and the Q3 is positive, they're actually attractive. So in this case, the force is actually acting this way. So that's F32. I think you can see from the symmetry of it that they're both tilted at the same angle, which from the horizontal would be this angle. But that's the same as this angle as well. So that would be that one as well. The reason why I'm saying this is you can see that the y components are exactly opposite each other. So the y component of F31 is positive, the y component of F32 is negative, and they're equal in size and equal opposite directions. So they're going to cancel out. But the actual x components, which point to the right, they both add to each other. So if I find the component in the x direction, I just double it and that'll be it. Okay. So I have to find that angle. And to do that, what I'm thinking is right here, I have 1.5. And right here, I have 4.0. And that's the angle that I want. Actually, let me get rid of this. One 1.5, 4.0, and let's call this angle alpha. That angle alpha is that angle. It's that angle, and it actually has to be the same as that angle as well. Notice that angle because the x-axis is horizontal, and the horizontal line up here through the 4 is being crossed by that, then this angle right here is equal to this angle right here. So those are both alpha. So what I'm going to say is F3B is equal to 2 times F31 x component, because F32 has the same x component as F31. So if I just multiply either 1 by 2, I'll get it. What I have to figure out is what alpha is, and alpha is equal to the inverse tangent. Alpha is equal to the inverse tangent of 4 over 1.5. So I'm going to say this is 2 times 4.43 times 10 to the 5th newtons times, now I've got to take the cosine of, when I take the inverse tangent of 4 divided by 1.5, oops, I get 69.44 degrees. So if I take 4.334 times 2. So I'm taking the 4.43 times 10 to the 5th times 2 times cosine 69.44. Way more sig figs than necessary. That gives me 3.11 times 10 to the 5th and it's to the right. God darn it. So I could write the actual force if I wanted to as 3.11 times 10 to the fifth newtons in the I hat direction, and that would be acceptable. Or I could just write it like this, and it's also acceptable. Okay. Any questions on that one? Okay, so that's sort of like the nasty problems that you have to deal with when you're doing this stuff. It's really good to get your practice with using symbols. So, being able to solve this as Q1, Q2 over 4 pi epsilon naught R squared or A squared or B squared, using symbols instead of numbers, that will come in really handy when you're trying to do some of the problems you'll see on the practice test. So, make sure you get started on that. Don't forget also, of course, we have, since you guys meet on Thursday, you're going to have a comprehensive face-to-face test on Thursday. I want to double check that that's what Miss Raskovic, or do y'all remember? Is that what Miss Raskovic told you? I'm pretty sure that's what her and I worked on. So I just wanted to remind you of that, but I'm trying to look in my email to make sure and my text messages. Okay. Oh, she must have sent it to me in an email, not in a text. Does anybody recall off the top of your head? Oh, Ava said yes. And I think, yeah, that was just now. So, okay, so Thursday's your test. What I've done is I made your second online test due at 10 a.m. that morning, and they're the same material. So I'm not making a separate practice test for the face-to-face one than from the online one. So you want to get your online one done by 10 a.m. Thursday morning. Well, actually, for you guys, I should have put that a little later. I should have put it like 2:15 p.m. I'll probably do that, but just make sure you get it done before you go to lab that day. And then during lab, you're going to take the face-to-face test. Anybody have any questions about these problems that I just worked? As you can tell, adding vectors is a thing that never goes away with physics or engineering. That's why, I've told you guys before that, it's sort of a rite of passage where you aren't supposed to make it through 241 and 242 if you can't add vectors. There's a few other things like that, but that's one of them. Obviously, converting units is another one. You're going to find out this semester we're also going to do line integrals and surface integrals. You might even do a curl and a divergence. Those aren't quite as critical, but it's a really good thing to make sure you guys can do line integrals and surface integrals. So anyways, we've gotten that, and I want to up the ante a little bit. So it turns out that this is not the best way to do things. We're actually calculating the force like we did with gravity, and we could just stop at that, but we have the same problem that Newton and Einstein had with gravity. Specifically, let me stop sharing for a second. Specifically, what we have is a scenario where I've got a charge here and a charge here, and these two are interacting via force, even though this charge can't touch this charge. That's called action at a distance. When Newton came up with his law of gravity, he said, hey, I've got this weird thing where, for instance, the sun reaches off across space and grabs a hold of the earth and pulls on it like it's actually attached, but there's no way they're actually attached. So I don't know how it's happening, but what I do know is that I can use this formula that I've derived and discovered, and that allows me to calculate, for instance, why Kepler's laws of planetary motion said, one, the planets orbit in elliptical orbits with the sun at one focus. I can prove that using Newton's law of gravity. Two, they sweep out equal areas in equal times. I can prove that using Newton's law of gravity. And three, the square of the period is proportional to the cube of the semi-major axis. I can prove that with Newton's law. So it's more than valuable. So we're just going to keep using it, and maybe one day we'll figure out what to do. Well, Einstein is what it took ultimately to figure out what to do with gravity, because it just didn't work out the way it did with the electric field and the magnetic field. But when someone came up, when Coulomb, which I told you is actually, Ben Franklin has a claim on Coulomb's law. Cavendish has a claim on Coulomb's law. I'm pretty sure that's the one that I found in my own research. And then Coulomb has a claim on Coulomb's law. All of them seem to have reached the same conclusion. I think Cavendish did it considerably earlier than Ben Franklin or Coulomb. And I think Ben Franklin did it earlier than Coulomb, but Coulomb would have been the last, and he's the one that published it. So ultimately, we call it Coulomb's law. But either way, the main thing is there's another way we could have done gravity, and your book did talk about that, like it's either in a footnote or at the end of the chapter or some other section. But what you can do is imagine that when I have let's take in terms of gravity, when I have the sun and then I have Earth, you could imagine that the sun creates an aura around it. And that aura we can call the gravitational field, right? So you can have this aura around the sun. And if you can compute what its effect is on the aura around it, you would call that the gravitational field. And then the Earth gets in that gravitational field, and all you have to do is take the gravitational field and apply it to the Earth. And the fact that there's an aura around the sun means that the sun's aura is actually touching the Earth, so it's no longer action at a distance. Okay, it's still a little, sweeping crap under the rugs and ignoring some details, but it turned out when we did that with the electric field, it worked just fine. Okay, we can get a lot of physics done assuming that that's it, and we don't really need quantum mechanics and all that stuff. There are cases where the quantum mechanics of electricity and magnetism comes into play, and we need it absolutely there. But the vast majority of stuff that electrical engineers do not require, quantum electrodynamics. So we can just work with Maxwell's equations, and that's what we're shooting towards. So that is one way to do it. Well, we know the formula for the gravitational force is G m1 m2 over r squared. So if you think about the force on the Earth as a result of the sun, you'd say the force is G, the gravitational constant, that's big G, the 6.67 times 10 to the negative 11th, times the mass of the sun, times the mass of the Earth, divided by the distance between them squared. Well, you want ultimately that force to work out to be that number. G, mass of the sun, mass of the Earth over r squared. So why not call this aura around the sun, let's say it has a magnitude given by G times the mass of the sun divided by the distance that you want to find out the electric field, or excuse me, the gravitational field out squared. So if you wanted to actually figure out what the force on the Earth is, you plug in the distance between the sun and the Earth into the little r where you had G times the mass of the sun over r squared. That gives you the field strength right there at the distance away that the Earth is. And then you take that, which is an actual field, and it would have units of newtons per kilogram because the force is in newtons, and the gravitational force did come out in newtons, but we just took out the mass of the sun, so it's left being short a factor of kilograms. So it's newtons per kilograms of the field. But now if you take the mass of the Earth and multiply it by that, you get the actual force. So that was how you'd want to do it. And when we tried that, it doesn't work out so well with gravity. So let me say, I'm going to go ahead and share my screen again. Let me show you not just in words, but let me show you in equations so you get some understanding of what I'm talking about. So here we say force of gravity on Earth due to sun. That is F equals G times the mass of the sun. That's the symbol we use for the sun, by the way, in astronomy. You do a circle with a dot in the middle for obvious reasons. And then times the mass of the earth, which is a circle with a plus in the middle, divided by r circle plus squared. Everybody agrees that's exactly the magnitude of the force. Does that make sense to everyone? Do y'all recall that from the gravity chapter? So we can say, for instance, imagine the aura around the sun is this fancy symbol G. That's what I'm making it. Okay. It fancy symbol G, and we're going to calculate that as G times the mass of the sun divided by r squared. So it's G as a function of r. Make that a little cooler. Okay. And if you actually wanted it vectorially, then you'd have to use x squared plus y squared plus z squared instead of r squared. And you'd have to put an x component, which would be x over x squared plus y squared plus z squared I hat, a y component, which would be y over x squared plus y squared plus z squared j hat, and a z component, which would be z over x squared plus y squared plus z squared k hat. So in principle, more generally, we would get g of x comma y comma z would be equal to the gravitational constant times the mass of the sun times, now we could say, actually, let's go ahead and do this. We're going to say x squared plus y squared plus z squared times x I hat negative plus negative y j hat plus negative z k hat. And the negatives are just forcing it to point back towards where the sun is, and we're treating the sun as if it's at the origin of coordinates. So that would be the aura or the gravitational field. Okay. Now, if you decided to say that F is equal to G of X comma Y comma Z times M, meaning you have to take the gravitational field and multiply it by the mass of the object as its position, then you would see that the force is now equal to G M this times M that over x squared plus y squared plus z squared negative x I hat minus y j hat minus k z k hat. And notice that formula gives exactly the formula that we had for the magnitude of the force. Y'all see that that is the same magnitude. The difference being, of course, we have x, y, and z now, and I made it general enough where we can put in the x, y, and z coordinate of the sun, of the earth at any point, and this will automatically give me the vector value. So that's what we mean when we say a field. A field is basically something that you assign a quantity for each position x comma y comma z. In this case, it's actually a vector field because when you put in the x comma y comma z, you get an actual vector out, and that's a vector gravitational field. And if you multiply a vector times a scalar, which is how you ultimately get the actual force, then you still get a vector. And in that case, it's the force acting on it. So we're going to do the same thing with the electric field. Does anybody have any questions on this? Does this make some sense, or is it just completely blowing you away? Anyone? All right. Well, that's a good spot because I'm getting ready to generalize it, and I'm going to do a hell of a problem that's going to knock your socks off to some extent. So let's take a break till 7 p.m. And when you come back, I'll finish talking about this, and then we'll solve that really big problem. I'm here if you have any questions. Anybody have any questions or anything? Got about a minute left before it's time to come back. All right, let's go ahead and get back. I took the time to sort of write out in a sentence form what we're doing next, just so you'd have this to go on. However, I'd actually expanded the screen and didn't realize it, so I wrote it as if I was running out of paper. So it's now smaller than it is. But let me go ahead and read what it is. I want to start back with what we were talking about. What we said as an analogy is taking gravity, which I assume you sort of understood a little bit better because y'all had that as one chapter in the 241 course. And the gravitational force equation from Newton is G m1 m2 over r squared. So if you wanted to calculate the gravitational force on the Earth, for instance, as a result of the sun, then it'd be G times the mass of the sun times the mass of the Earth divided by the distance between the Earth and the sun squared. So instead of thinking as if some magical force is reaching out across space and grabbing the Earth, even though there's not physically anything touching the two, we imagine that the sun creates a field around it, and I called it an aura, A-U-R-A, which I have no idea now if that's the right spelling of that word, but anyways, but we imagine a field around the sun that is created because the sun's mass has the tendency to pull other masses towards it. And the way you would use that field is you figure out some kind of formula where you could stick in information and out pops the force. Well, what I argued that formula would be is this weird looking lowercase g that sort of looks like a mix between a lowercase g and a capital G. I'm calling that the gravitational field, and I initially drew it as if it's not a vector quantity. That's why you see no I hats, j hats, and k hats on this version. Now, technically, when I went to this version, I did include a vector. So in principle, I should actually put a vector symbol up there, and that now allows it to account for this. What I was trying to argue, so you'd understand the nuts and the bolts, is that field, G, depends on exactly where you put another mass. So it depends on a coordinate system. And what I'm picturing here is that the coordinate system is like this, where you have an x-axis, a y-axis, and a z-axis. And then right at the origin is the sun. So to account for how far away the planet is that is being affected by the sun, we need to know the x, the y, the z of the sun. And that's why you see the x, the y, and the z in it. Notice the distance is supposed to be the square root of x squared plus y squared plus z squared, according to the Pythagorean theorem. But then we're supposed to take that distance and square it, so it just becomes x squared plus y squared plus z squared. And that gives us, if we put in x, y, z, that gives us a magnitude of the field by taking g, the gravitational constant, times m for the sun, divided by the distance away squared. And then if you want the direction, you have to multiply it by the x coordinate and I hat in the negative direction because it's an attractive force. It's always pulling it towards the origin. That's why I had to have a negative. And you have to put in the y and you have to put in the z as well. And all of that gives you not only the magnitude of the field, which is in newtons per Coulomb, or excuse me, per kilogram, So that's the actual units that we're getting out from this formula. So I've got to put in an X, a Y, and a Z just to find out what the field is at a particular X, Y, Z position. And since the formula had not only the distance and the mass of the sun in G, it also had the mass of the object being affected by it. I also have to multiply this quantity by the mass of the Earth or whatever planet I'm using. So ultimately what you get is G, M sun, M mass, XYZ for where the Earth is, and XYZ for where the Earth is. And by doing that, I now have exactly the right magnitude as given by this. Don't worry too much about the X, the Y, and the Z, but it does work out to be that way because you have to know not only how far it is, but you have to assign it a position in space so that it points in the right direction. So that's why I have the X, Y, Z in there. But that's ultimately how you do it. So now that I've recapped that, let me go tell you in sentence form how I'm going to deal with the electric field. I said, now we're going to follow a similar process for the electric force. We will imagine one charge, I'm going to call that capital Q, by the way, can create an electric field E of X, Y, Z, and that we can then find out the force that the electric field applies to a charge lowercase q. Notice I hadn't thought of putting a lowercase q in until after the fact. By plugging in the position XYZ of the particle into E of XYZ and then multiplying that by the charge Q. So just like I did before, I still got to plug in the X, Y, and Z for where the particle is going to be. That's got to be plugged into the field. And then I've got to take it and multiply it by the mass of the particle at that particular spot, and then that would give me the gravitational force. But in this case, I've got to plug in the X, Y, and Z for where the particle is going to be, and then multiply it by the charge Q. So in principle, we actually have to imagine the case where the charge Q is so small that it does not appreciably affect the electric field. So that the electric field that I call E of XYZ is technically the limit as Q approaches zero of the force F of XYZ divided by Q. Now here I'm just plugging in for force, I'm plugging in Coulomb's law. So I still have the limit as Q approaches zero. I still have the limit as Q approaches zero. And now I have Coulomb's law right here. Remember, Coulomb's law is K, but ultimately K is the same thing. Let me write that real quick. K is defined to be 1 over 4 pi epsilon naught, which I showed you already, but I just want to remind you. So that's why the 4 pi epsilon naught's down there. But you can see I have the X, the Y, the Z, and all that good stuff still in there. But what I'm actually doing is I'm going to take that force, which is Q times Q over 4 pi epsilon naught over R squared, and I'm going to divide out the actual Q. So I'm picturing two charges, a big Q and a little q, and I'm imagining the big Q is creating the aura or the field, and the little q is being affected by it. So what this means is you have a formula that E is equal to F over Q. In principle, it really is supposed to be that limit, but you can still use the formula as if it's this, but that also gives you another formula. That means F, the force, is equal to Q times the electric field. So if you take the time to actually calculate or know the electric field, if you want the force out of it, all you have to do is multiply the charge times the electric field. Now, in principle, you also have to feed the electric field the actual position X, Y, and Z, but that's almost always done automatically without any troubles. So those are the two big formulas that we're using now. And from this, we get the electric field according to Coulomb's law. Electric field Coulomb is equal to Q over 4 pi epsilon naught R squared. And this is E of R, where R is some distance away from the charge Q. So now I have a general formula for the electric field. Notice it's just a scalar field, okay? I didn't actually put the vector stuff in there because it turns out it's really easy to deal with the scalar field. Then you just have to remember that the force actually acts along a line connecting the center of charge of the big Q to the center of charge of the little q. So those are our big formulas. Does everybody follow that? Anybody have any questions on that? So if we went back to that example that I did earlier, this one right here, I could just calculate the electric field at point A, and I tell you exactly what it is. For instance, when we added these two forces, F31 and F32, I got a magnitude of 3.140 times 10 to the fifth. If I just took that 3.140 times 10 to the fifth and divided it by 3 times 10 to the negative third coulombs, because that's what Q3 is, then that would give me the electric field at A. Its magnitude would be 3.140 e to the fifth divided by 3 e to the negative 3. That would give me 1.05 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. So the electric field will be 1.05 times 10 to the 8 newtons per coulomb. Does everybody see what I'm saying about that? So just taking this number right here and dividing it by this number right here means I'm pretending that these two charges, Q1 and Q2, created an electric field, E, and that electric field right here is this number divided by that number, and that gives you the magnitude that's 1.05 times 10 to the 8th. And in fact, it points in exactly the direction of the force. So it's also at that 51.8 degrees. I could also do it for this spot here, which we call spot B. Again, it'd be the exact same magnitude because I'm just dividing the force, which in this case would be 2 times 4.43 times 10 to the fifth times cosine of all this. I'm going to take this number, 3.11 times 10 to the fifth, and divide it by 3.0 times 10 to the negative third. And that's going to give me the magnitude of the electric field at this spot in newtons per coulomb. And in fact, the direction would be to the right. So hopefully that's enough to set it in there. I want to go ahead and let you know that the actual units of the electric field is equal to newtons per coulomb. But ultimately, we're also going to find it's going to be volts per meter. So we don't know this yet. But we will in 2 chapters. Okay, so right now we're thinking the unit is newtons per coulomb, and that's fine. Later we're going to work that out to be volts per meter, and that's fine too. So now that we have that, I want to show you something. Let's draw a coordinate system. This is going to be my x-axis, this is going to be my y-axis, and this is going to be my z-axis. Now, what I could do is I could put a charge Q that's actually a macroscopic charge, so it's not necessarily a point particle, and I could give it a vector that points to its center of charge, which is that little point in space, and that vector would be called R sub Q. Okay. Now it creates, because it exists and it has a charge Q, it creates an aura around it called the electric field. Okay. Now I could, in principle, have a point charge out here, lowercase q, and then the vector pointing from the origin to it would be r sub little q. Okay. Now, the electric field and also Coulomb's law of force dictate that the actual force, and therefore the electric field, has to be applied along the line connecting the center of charge of Q to the center of charge of little q. So I could, for instance, say there's a line that goes from the tip of R big Q through the tip of R little q, like that, okay? And somewhere along that line has to be the force and the electric field. If we go on the assumption that Q is positive, and we agree that let's not do that symbol, that the electric field direction is the direction that a positive charge would be compelled to move then E will point along the red line from Q toward little q. Does that make sense to everyone? We're going with a convention. This is something that all the physicists in the world have agreed to. And the convention is that the electric field at any particular point points in the direction that if you stuck a positive charge right there at that point, it would be compelled to move in a certain direction. That direction is the direction of the electric field. So if you imagine putting a positive charge at little q, and you already made the assumption that big Q is positive, you would see that the force, or the electric field in this case, is in fact along this direction. Okay. Can anybody think of a way you could use RQ and R little q to compute what that vector there is? That vector is the electric field. Can you tell me a mathematical operation you can do between R big Q and R little q to get that specific E vector? And I'll put that little symbol there just to say that this is not necessarily the right size. So I'm just saying this is proportional to E, and therefore it points parallel to E, but the size doesn't necessarily matter.
Is it R little q minus RQ?
Excellent. Good job. Yeah, you're like only the second or third person that's ever gotten that answer right. Good job. So the actual direction of E field is parallel to R little q minus R big Q. Okay. So that's great. That means now that you know the direction, you can multiply that vector times the magnitude of the force, and you will sort of have the force or the electric field, whichever one you want to compute, but you're off by a factor of the length of that vector. Because, of course, it's not a unit vector. If it's a unit vector, it'd be great. Well, the way you make a unit vector, actually, do any of you know how to make a unit vector out of a vector?
Don't you divide by the magnitude of the vector?
Exactly. And by the way, no one's expected to know that. That's a wonderful thing that you do, but I just want to make sure everybody understands that you didn't have to know that. We're supposed to be teaching you that in this class, so it's perfectly fine if you didn't get it. You're not being left behind. It's just a matter of some of us learned it a little earlier than others. So yeah, absolutely. If you took RQ minus R big Q and you divided it by the magnitude of RQ minus R big Q, then you'd have a unit vector that's parallel to RQ minus R big Q. All of that helps me make a vectorial form of Coulomb's law for the electric field. So I'm going to show you exactly what that is, and then we're going to use it. So what we know is that the electric field is given by Q over 4 pi epsilon naught R squared. That's the magnitude of the formula, right? Ideally, we'd like to make a vector. So I'm going to show you how to make that vector, and I'm going to use the stuff we just figured out. But in doing so, I've got to sort of play around with it a little bit and make some sense. So first off, I need to explain to you how we're going to actually treat this Q. So the Q that's actually causing the field, causing the electric field, Q that creates the E field, that can be given using calculus by several different ways, because it's not going to be very helpful for us to only find the forces between 2 point particles. What we'd ideally like to do is imagine a spherical distribution of charges, or a cylindrical distribution of charges, or a flat plane of charges. So we need some way of dividing that up into infinitesimal charges, and then know how to deal with those. So what we're going to do is we're going to say Q can be a couple different values. Q can be given by basically a lambda factor times dl, meaning if we wanted to make a infinitely thin but also very, very long charge distribution. So imagine like a fission string that, instead of being made of fission string, of whatever that material is for fission string, imagine it was made of a string of little positive charges. If you take the charge per unit length, which is what the lambda represents, and multiply it by the little differential length dl, then you'll get the amount of charge in that little bit of length dl. But if you wanted that charge to not be one-dimensional like that, then maybe you want it two-dimensional, in which case you're going to say it's sigma times dA, where sigma is the charge per unit area, and dA is a differential area element, like a dx times dy, or like a 4 times dy. Or if you wanted it to be a three-dimensional object, then you would call it rho times dv, where v is a differential volume element. And another way of saying that is lambda is equal to dq over dl, sigma is equal to dq over dA, and rho is equal to dq over dV. And we could say lambda has units of coulombs per meter. Sigma has units of coulombs per square meter. And rho has units of coulombs per meter cubed. Okay. So that's sort of the critical thing that we have to know is we have to be able to put together a bunch of little infinitesimal charges dq, and I just call it dq, to make a charge q. So with all of this comes some special stuff. These equations are very important, but also it means q is equal to the integral of dq, which could be the integral of lambda dl, or it could be the integral of sigma dA, or it could be the integral of rho dV. So this is another formula that we're going to use not only in this chapter, but virtually every chapter that comes after this up until we get to 31. So that's sort of the groundwork that we have to do in addition to what you figured out, RQ minus R little q. That's important as well, okay? Or excuse me, R little q minus R big Q. So all of that's relevant. So what we're going to do now is I'm going to draw another coordinate system just to make it all sit in our head nice and neatly. I'm going to say my coordinate system is this one, this one, this one. And now I'm going to say this is my x-axis, this is my y-axis, this is my z-axis. And I am going to take a blob of charge, q, which equals the integral of dq, okay? That's going to have, in fact, I'm trying to make you guys picture that it could, in fact, be three-dimensional by drawing those little lines on it. And then inside of here is the differential charge element, or excuse me, is the center of charge. Or more specifically, it could be a single dq. So I'm going to call this r, this vector right here is going to be r sub dq. It's the vector that points to the differential charge element that's relevant at that particular point in your integration of dq. Okay. It could also point to ultimately just to the center of charge of it. But what we have to do is we have to allow this dq to hit all the infinitesimal points in that kidney bean shape. Okay. Now I'm going to write over here that we have a charge q, and because of that charge q, we have a vector that points to it that is rq. Okay. So what we can do is we can say E, the differential segment of the electric field. In other words, the electric field that's due to a very infinitesimal section of charge dq is dE. And that's going to be given by dq. Actually, I should probably call it, since I called that other one lowercase q, I probably should call this one upper q. So I'm going to change this. Everybody see that little q that I just erased? I'm going to call that d big Q just for the heck of it. It's sort of the same thing as saying R, that's d big Q. Both of those are acceptable. So just to keep us from getting confused as to which one's which, I'm going to go ahead and call this d big Q. Okay. And that's going to be over 4 pi epsilon naught. Now I need something to express the distance between dq and rq. So in other words, between the differential charge element d big Q and the charge little q. we've already figured out from, I think it was Sebastian, let us know that that vector is in fact RQ minus RDQ. So what I'm going to do is down here in the bottom, instead of just writing randomly R squared, I'm going to write RQ minus RDQ. And then I'm going to put absolute value bars on it. And that means I'm now saying the magnitude, so it's not a vector quantity. And of course, it needs to be squared because that's what Coulomb's law is. It's Q over 4 pi epsilon naught R squared. But notice it's just like the form that I have here. Everybody see it's Q over 4 pi epsilon naught R squared, but it's not a vector yet. So really to make a vector, I still gotta fix that. So let me start by cleaning that symbol up. That turned out to be crap. So there's my DQ. Now I need a vector that's exactly parallel to RQ minus RDQ. So I'm just going to use RQ minus RDQ. So I'm going to say RQ minus RDQ. That's the actual vector. But notice I just multiplied the magnitude, which was right on the money before I wrote that. Before I wrote this magnitude was perfectly the same as that. But now that I have that, it's up by a factor of R. It's up by a factor of this little guy, just R, not R squared. So what I really want to do is multiply by a unit vector, which Sebastian told us was the same thing as taking the vector and dividing it by its magnitude. So I'm going to put RQ minus RDQ right there. So now this whole quantity right here is essentially what I would call RQ minus RDQ hat. So it's a unit vector. So ultimately, our answer is going to be this. The differential electric field element is dq times rq minus rdq over 4 pi epsilon naught times the magnitude rq minus rdq. Now it has to be cubed because it was already squared, but I had to add a third one down there to make it a unit vector. So that's our final answer. That's the fundamental equation for calculating the electric field due to a charge distribution. Okay. You'll notice that that is actually on our equation sheet that I gave you. Now I'm going to use that to actually calculate the electric field due to an infinite line charge. So we're going to call this example 3, I think, because I think we only did 2 examples so far. Yes, we're going to call this example 3. So that might sound kind of wordy and weird, but I'm going to draw it and that'll hopefully fix everything. So I'm going to draw a coordinate system like that. And let's draw this to be the x-axis. So this is going to be my x-axis. And let's make this one, because it'll come in handy, I'm going to make that the z-axis. There's a good reason for that. I could have called this one the y-axis, but it really doesn't matter too much. What I'm going to do is imagine that I have basically an infinitely long, infinitely thin distribution of charges that goes on for infinity this way and this way. Okay. And then I'm going to go over here to a distance that I'm just going to call R. And I'm going to say, this is the point P at which I wish to know the E field. So I'm really calculating the E field at a point, and I've been calling the point basically where you'd put the charge little q. So little q can be represented as the point P, or it could just be a little q. I'm going to use it as the P here. So that's the P. And what we know is, for our solution, we need to know that dE is equal to dQ times R. Now, in this case, because I don't have a charged little q, I could just put P there and everything will be fine, minus R dQ over 4 pi epsilon naught times RP minus R dQ cubed. That's the formula we're going to use. And remember, R either points to the little charge Q that's going to be affected by the electric field, or to the point P at which we wish to know the electric field. So just for the record, I'm going to go ahead and draw RP as this vector right here. So this vector is RP. Can anyone tell me what RP would be using, let's say, I hats, J hats, and K hats? Remember, it's a vector that points from the origin to the position P. And I told you in the problem that the position P is a distance R away from the wire, the infinitely long charged wire. Anybody want to try now to give me the RP vector? You're going to shoot yourself when you find out how easy it is. Okay. So we know it points to the right, which is our X direction. So it's going to be in the I hat direction. And we know its length is R. So RP is just going to be R I hat. Okay. Now I'm going to go a little further. I'm going to take, and normally you try to do this, you find a representative DQ. And it should be like in the first quadrant, or on the x-axis, or on the positive x-axis, or on the positive y-axis. That way you don't have to deal with negative signs and all that. So I'm going to call this right here dq, and it's going to be lambda times dl. And that means that this little length is dl, which is really just dy. Okay, so I now know what dq is. dq is going to be lambda dy. And now, since I pointed out the dq, I can also write down what r dq is. Let's use a blue vector for that one. So here's the vector from the origin that points to dq. So this is the vector r dq. Can anybody tell me what r dq is in terms of I hats, j hats, and k hats and all that good stuff? Notice that is along the z-axis, so that might help you. I did not explicitly write the distance, but I hope you can figure out what variable to call it. Anyone? Okay. Just because we only got about 10 minutes left, I'm going to tell you that that distance is along the z-axis, so it's actually just going to be plain z, and I'm going to call it zk hat because it points in the positive k direction. You can see, hopefully, that rp minus rdq is really, let's use this color, is really this vector right here. So that vector right, dang it. That vector right there is rp minus rdq. And we can now compute that rp minus rdq is in fact equal to ri hat minus zk hat. And we now have rp minus rdq. So we've gotten this part right here worked out. We've got this part right here worked out because that's dq is equal to lambda dy. And all we need now is this magnitude down here, rp minus rdq. Anybody want to take a guess at what the magnitude of rp minus rdq is? Anyone? That's it. Okay. So we can now say E is equal to the integral of dE, which equals 1 over 4 pi epsilon naught. That part I know is going to be a constant, so I just went ahead and pulled it out in front. And I'm going to integrate my dq, which is lambda. Oop, I said dy. That's supposed to be lambda dz. Everybody catch that? Or did anybody catch that? This is supposed to be lambda dz, not dy. And that means over here, this is supposed to be lambda dz, not dy. I think that's all the places where I screwed it up. Yeah, that's it. So I've got a lambda dz on the top. And then I've got a ri hat minus zk hat up top. The 4 pi epsilon naught is already gone, but I have a rp minus rdq that's got to be cubed. So that's going to be r squared plus z squared to the 1/2 power, but raised to the 3 power. So that's going to be to the 3/2 power. Now we've got to integrate that, which is not going to be as bad as you might think. Okay. So what I can do is I can say there's going to be a part that's due to the I hat, and then there's going to be a part that's due to the K hat. So what I can see is I have one integral that's going to be 1 over 4 pi epsilon naught times the integral lambda dz, or let's write it this way. Let's say lambda times r times dz times I hat over r squared plus z squared to the 3/2. That's one integral. I'm going to call that integral sub x. And then I have another integral. I'm going to call it integral sub z. And this one's going to be 1 over 4 pi epsilon naught integral lambda. There's going to be a negative in front of it, and there's going to be a z. And the negative came from the negative that was right here, in case anybody's wondering. Everybody see that negative? And it's going to be that times dz, and then times k hat. And then all of that's going to be the square root of r squared plus z squared. Oops. I'll do it like this, to the 3/2 power. So those are the two integrals we're going to do. Now, what I can tell you is, notice we're going to integrate all this junk. And in this case, I'm going to integrate from negative infinity, z equals negative infinity, to z equals positive infinity. So I'm going to say negative infinity to positive infinity, negative infinity to positive infinity. So you can see that this vector we just made, this rp minus rdq, that vector is really important. It's going to have, obviously, an x component and a z component. Sorry, I'm trying to make this a little cleaner. Okay, it's going to have this I term that we see right here, which is actually this one. And we're going to have this k term right here, which is this one. Okay, if you look, what we mean by this is, let me draw another color. And I don't know what happened to my color stuff. Oh, there it is. Okay, let me draw a different color. I'm going to say, no, I don't want to do purple. Purple already got. I'm going to say this lime green. So this right here, darn it, it makes me so mad. That's my DE vector. So you see the DE vector has, I can put it such that it has a x component and a z component. And you notice that when I go over here and do this little part, I'm going to get yet a DE that's like that. And that's going to have an x component and a y component, or a z component. But I think you can see by the symmetry of it that the two z components are going to cancel each other out. So we expect this integral right here to be 0. And we can integrate that to show it, but the other one's not. In fact, the other one's going to, I could actually do it from 0 to infinity and then multiply it by 2, because the symmetry of it is that the x component is the same in both cases. So let's start off with this integral. I'm going to say I sub x is equal to, which is technically a vector quantity. I'm now going to say lambda over 4 pi epsilon naught. The r is actually a constant, so I'm going to pull that out in front. And this is going to be the integral of, and I'll pull the I hat in front, because I hat, j hat, and k hat are the wonderful unit vectors that you can actually pass through derivatives and integrals without any loss of anything. So what I have here is dz. And what I'm going to do is I'm going to make a substitution. I'm going to say let z equal r tangent theta, which means that dz is equal to r secant squared theta d theta. Okay. When I do this, watch what happens. I now have r squared plus r squared tangent squared theta, all that raised to the 3/2, like that. You can clearly make that r squared come out in front, and it'd be r squared times 1 plus tangent squared theta. And everybody knows that 1 plus tangent theta, 1 plus tangent squared, is equal to, anyone? Secant squared theta. So now what we get from that trig substitution is I get lambda times r over 4 pi epsilon naught times I hat times the integral. Now the dz is going to become r secant squared theta d theta. And then down here, we've got a r squared times the secant squared theta, all that raised to the 3/2. So the r squared raised to the 3/2 becomes a r cubed in the bottom. And we've already got an r up top. So it's going to be lambda r squared over 4 pi epsilon naught r cubed, like that, times dot, 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 which I don't have enough room, so I'm going to go to the next line. Notice the r squared cancels out with all but one of those. So I now have, and I also left off the I hat, but that's okay. It's lambda I hat over 4 pi epsilon naught r integral. Now what we have is, notice the secant squared in the bottom is raised to the 3/2, so that's going to be secant cubed. And then there's a secant squared up top, so that's going to cancel out completely and just leave a secant in the bottom. So now I have d theta over secant theta. And if we think about the triangle that I get from that trig substitution, what we had was tangent theta is equal to z over r, and that would be theta, and this would be the square root of r squared plus z squared. So I now can integrate from theta equals 0, well, actually from theta equals negative pi over 2 to theta equals pi over 2. And that's the integral that I'm going to do. In this case, it's going to become lambda I hat over 4 pi epsilon naught r. And I should sort of cordon this off so we won't get them confused for each other. Now it's going to be the integral. I'll put a 2 there and say it's the integral from 0 to pi over 2. Now it's the integral of cosine theta d theta. And of course, the derivative of sine is cosine, so the integral of cosine is sine. So I end up getting equals 2 lambda I hat over 4 pi epsilon naught r. Okay, the 2 was out in front. That's where the 2 came up there. And I end up getting the sine of pi over 2 minus the sine of 0. And of course, the sine of pi over 2 is just 1. Darn it. The sine of pi over 2 is just 1, and the sine of 0 is 0, like that. So basically, my answer is equal to lambda over 2 pi epsilon naught r in the I hat direction. And that's I sub x, like that. Now, we can actually go ahead and do the same substitution, and what we'd find out is that other integral iz is 0. So we can now say that the electric field E is actually equal to lambda over 2 pi epsilon naught r in the I hat direction. And that's the answer in its entirety. Okay. You can look, I have links to this problem worked over and over again in your module, and you'll find me work it out and you'll find me computing the other part of the integral. But that's basically the second worst thing you'll see the entire semester of all the calculus you're going to do. So we're done. You guys, of course, are free to go. Thanks for coming. I'm going to wait for the last person to leave in case you have any questions. So feel free. I know this is really hard. Everything I just showed you might have knocked you down and made you feel like you don't know what's going on. That's perfectly fine. This is very normal. It happens all the time in physics and engineering and stuff like that. So don't worry about it. What you want to try to do is go back over it, look how I did it, look at this video, then look in your book. Your book did exactly the same example, but it did it without the gory details of all the integrals, but they were being very ingenious. And that ingeniousness is not an easy thing to come by. So I think it's better to show you the details. And then maybe after you understand the details, you can make more sense of the short, easier, quote unquote, way. Okay. Now I didn't do the other one just because I ran out of time, but the other integral does turn out to be 0. You can look at it and see that it's obviously an odd function, because if you replace z with negative z, you get the negative integrand that you had when z was positive z, and an integral of an odd function over a symmetric range is always 0. So that's one of many ways that it's going to be 0. I also showed you physically that the z components are going to cancel each other out by the symmetry, so that's another way. And then you can also compute the integral, and that's the third way. But if you have any questions, go ahead and stick around and ask, but you're free to go. And remember, you do have a test on that's due coming Thursday. So make sure you get that knocked out. And then you have a face-to-face test on Thursday. It will not include this, by the way. No questions? All right. I think I might actually integrate that last term on the notes, so you at least have it in the notes. So let me just do that real quick. You guys are free to go. Like I said, I'm going to go ahead and finish out the other term, at least in the notes. So now what I'm going to do is I will try to copy this part. So I'm going to use this little line right here. I'm going to say copy. Now I'm going to put it back here and I'm going to say paste. Okay. Now in this case, I don't actually have to use a trig substitution, because I have a z squared in the bottom and I have a z up top. So I can actually do a much simpler substitution. I can say let r squared plus z squared equal u, implies du is equal to 2z dz. So now I can go ahead and say this is going to be negative k hat. I'm just replacing the 1 with the k hat that's on the right hand side, over 4 pi epsilon naught. I'm going to put the lambda over here because I know that's going to happen. And what I'm going to do is I'm going to multiply by 1/2. And then inside the integral, I'm going to multiply by 2, so that I have 2z dz. And then, of course, over that, I will have u to the 3/2 power. I'm going to go carry this out another line, and it's going to be negative lambda k over 8 pi epsilon naught times the integral of u to the negative 3/2 du, because 2z dz is du. Now I've got lambda k over 8 pi epsilon naught. And of course, the integral of u to the negative 3 halves is u to the negative 3 halves plus 1, which would be 2 halves. So 2 halves minus 3 halves is positive 1 half. So I'm going to get u to the 1 half divided by 1 half. And that's going to be evaluated from z approaching negative infinity to z approaching infinity. So now I'm going to go back to what my substitution was. I'm going to say negative lambda k hat over 8 pi epsilon naught. And what I get is the square root of r squared plus z squared to the 1 half. And I'm going to do from negative infinity to positive infinity, which means we're basically going to have a take a limit process. So when I actually do this, I get negative lambda k hat over 8 pi epsilon naught. And then I'm going to say take the limit as z approaches infinity of the square root of r squared plus z squared minus the limit as z approaches negative infinity of the square root of r squared plus, oh, that's really bad looking, r squared plus z squared. And you can see that the limit as z approaches infinity, z is going to become really big compared to r, so it's just the square root of z squared, which just becomes z. So this one goes to z, and this one, because it's squared, also goes to z. So we end up getting z minus z, which is 0. Okay, so that's another way of doing it. But notice the integrand which was specifically z over the square root of r squared plus z squared, that integrand is equal to I of z, say, is, darn it, is an odd function because, darn it, because or excuse me, because I of negative z is equal to negative z over the square root r squared plus negative z squared, which equals negative of z over the square root r squared plus z squared, which equals negative I of z. Therefore, the integral of I of z from negative infinity to positive infinity is equal to 0 because 0 to infinity gives the negative of the integral from negative infinity. Ooh, excuse me. Therefore, the integral, let's do it this way. So let's do it this way. I'm going to do this. I'm going to say the integral from negative infinity to 0 gives the negative of the integral from 0 to infinity of I of z. Oh, that's, yeah, I already started writing that. So let me do this. Because, so this is what I'm saying here. Because the integral from 0 to infinity of I of z gives the negative of the integral of negative infinity to 0 of I of z, so that so that's another way of doing it. Of course, we also used physical arguments and symmetry to conclude the integral is 0. All right, that's it. Thanks again, everyone. Talk to you later. Have a good one. Bye-bye.